Hi, in this video we will learn about a notion for matrices called rank of a matrix, and we will study how the rank of the coefficient matrix of a linear system is related to the number of free variables in the solutions of that system. This is the rank theorem. Okay, so let us start with the definition of the rank. What is the rank of a matrix A? Well, this is a number and we denote it by just write rank A is, what kind of number is that? Well, it is the number of non-zero rows in not A itself, but its row echelon form. In other words, if someone gives you a matrix and asks you to find the rank of that matrix, you have to reduce it to row echelon form and then count the number of non-zero rows. Let's see this in some examples. Here I have a few examples, and the first one, I see it is in row echelon form. Yes, so if it is in row echelon form, then rank of the matrix, let me call it A, is going to be equal to number of the non-zero rows: 1 non-zero row, 2 non-zero row, and 3 non-zero row. How about this other one? Well, okay, so is it in row echelon form? Why I'm asking if it is in row echelon form? Because if it is not, we have to reduce it to row echelon form and then count the number of non-zero rows. Here, this matrix, this matrix is in row echelon form. And as a result of that, the rank of A is equal to number of non-zero rows, which are 2. The third example, is this in row echelon form? Well, see, this is the first leading entry of the first row. Below that, this one is 0, but this is not 0. So that means it's not in row echelon form. In terms of rank, you cannot count the number of non-zero rows here. You have to reduce it to row echelon form, then count the number of non-zero entries. In this case, I want to get rid of that 2. Well, we can do that by simply replacing R3 by R3 minus R1. And this gives us 2, -1, -1. 0, 1, 2, these don't change. And for the last one, this will be 0. 0 minus -1 is 1. 1 minus -2, 1 minus -1 is 2. Yes, very nice. Then the next thing is, okay, this can be our next leading entry, and then everything below that must be 0. So here, to make that one 0, we have to do R3 minus R2. This way we get 2, -1, -1, and 0, 1, 2, and this gives us 1 minus 1, 2 minus 2. And as you can see, although the original matrix had 3 non-zero entries, its row echelon form has only 2. So that means that the rank of this third matrix, let me call it C, is just 2. And let's do one more example here. How about the rank of this one? Well, obviously this is not in row echelon form. I can take this, make these ones 3, 0. So for that, R2 minus R1 is good 1. R3 plus R1 is also good 1. And the middle one, for that one, we have to go minus 3 times R1 added to R3. So let's do this one, 1, 0. And here will be just subtract, yes, 0, negative 1. And this guy here will be 0. Well, there's nothing up there, negative 2 stays there. And then down there, this is just 0 and 2. Very nice. This is there. Now I can choose this one and make this 2, 0. And here, R3 minus 2R2 and R4. Oh, here this must be R4. And this one's R4 plus 2R2. R1 and R2 we don't change. Well, however, these two will make this guy 0, this guy 0, 0. Now, it is in row echelon form. It's actually in reduced row echelon. Well, no, it is in just echelon form, row echelon form. And this is the number of non-zero rows is 2. So rank of this fourth matrix, let me write it by D, is equal to 2. And these last two examples show that you have to do row echelon form. The number of non-zero rows may change as you do the reduction. Okay, very nice. So having all these things, now let's just move toward the cases that A is the coefficient matrix. So let A be the coefficient matrix of a linear system. So what is important about the coefficients of coefficient matrix? First thing is that number of columns of coefficient matrix, columns of A, is equal to number of variables of every equation gives us one row, every variable gives us one column in the coefficient matrix. That's the first thing. The second thing was that when you row reduce the matrix, the number of non-zero, let me write here, non-zero rows in row echelon form, this is in general for all matrices, this is equal to exactly number of non-zero leading entries. Because every non-zero row starts with a leading entry, yes? So you just count those ones. But why do I count those ones? Because this is now related to the number of columns. So the number of, since in each column we can have only one leading entry, then the number of columns with leading entry of some row is going to be equal to number of non-zero rows. In other words, what we have here is that, well, we found another way of finding or counting the rank of the matrix. Count the number of columns with leading entry. Okay, now this last thing is where the proof of the rank theorem is going to be completed. Remember that when we solve a system, so if the system is consistent, it means that we know at least there is one solution. Then the number of free variables, most of the time I mention this as number of parameters in the solutions, yes, is equal to the number of columns without entry, leading entry, yes. But we know that the number of columns with leading entry is rank. Now the number of columns without leading entry is going to be, well, the total number of columns minus number of columns with leading entry. And this is nothing but that this piece we just figured out, this is rank of A. The number of columns of A, on the other hand, is number of variables of the system, yes? And what we proved is that number of free variables in the solutions of a consistent system of linear equation is equal to number of variables minus rank A. This is what is called the rank test, the rank theorem. It is important for a consistent system of linear equation with coefficient matrix A. This is what we have. So let me put this in the box. This is what we have. Number of free variables in the solution of that system is equal to number of variables minus rank of the coefficient matrix. Here I have to emphasize again, remark or note the consistency of the SLE in the rank theorem is absolutely necessary condition, absolutely required condition. It means that you cannot say anything about the relation between the free variables and so on if you don't know the matrix is consistent or not. Okay, and when this comes in, then you always have this extra condition you have to check, unless you know that the system is not going to be inconsistent. You see, system has two parts. One is the coefficient part. The other part is the constant term parts, yes. And inconsistency comes when you row reduce and you get a matrix to the case that the a row in the coefficient part is 0, on the other hand is non-zero. So if we start with a matrix, with the system of linear equation, which has all 0 for the constant terms, we know that always it is consistent. So let me just write as a remark: if all the constant terms of the equations are 0, then the system is consistent. And actually, such a system which has all the constant terms equal to 0, such a system is called homogeneous system. So it is, the name we have is, so such a system is called a homogeneous In other words, when you write the augmented matrix, you will have the coefficient matrix. The other side, everything will be 0. Another way of seeing that a homogeneous system is consistent is that while always 0, 0, 0, the vector 0, 0, 0 is a solution for the for any homogeneous system. That's another way of seeing that it is consistent. We have at least one solution, 0, 0, 0, the origin, the 0 vector. Now, while it may have more solution, but at least it has one solution, it means that it is consistent. Okay, so now if we apply the rank theorem for the for this homogeneous systems, then we know that as a result, corollary, so for any homogeneous system with coefficient matrix A, the number of free variables or parameters is equal to number of variables minus rank of A. Again, when you work with homogeneous systems, you don't need to be worried about the consistency of the system. And another funny and nice thing is that if we have more variables than equations, then we are going to always have free variables. So this is the theorem that I will finish my video with. So if A0 is a homogeneous system with m equations and n variables, and m is less than, and if m is less than n, it means that the number of variables is bigger than number of the equations, then the system has infinitely many solutions. So in the homogeneous system, if the number of the equations is less than number of the variables, we are going to have infinitely many solutions, and that's because of the rank theorem. You see, the number of variables, the rank is at most equal to the number of equations, number of the rows, yes? So if number of variables is bigger than number of equations, as a result, number of variables will be bigger than, let me write it down, variables is bigger than number of equations, implies that, well, see, the number of equations is a cap for rank A, because what do? We count the number of non-zero rows in the row echelon form. It cannot be more than the number of equations, yes? So if we have more variables than the equations, that means that variables are bigger than, strictly bigger than rank of A. That means that we will have free variables. Free variables are going to be bigger than 0. That means that we have at least one free variable, and free variable means that we have infinitely many solutions. Okay, so just quick overview. What we did here in this video is that, okay, define what is the rank, did some examples, and then rank theorem is studied, and then we saw that how homogeneous systems come into the picture.